Oh, can you hear me? Okay. Well, it's my pleasure to introduce Sarah Petersen, who's going to tell us about Ravenel-Wilson-Hopf-Ring methods in C2 equivariant homotopy theory and the HF2 homology of C2 equivariant Eilenberg.
Thank you for the introduction, JD, and thank you to the organizers for the invitation to speak. So I'd like to start off this talk by talking about some of the non-equivariant background that motivates my approach to the computation of the HF2 homology of C2 equivariant Eilenberg-MacLean spaces. So a good place to start is with recalling the definition of a Hopf ring. So a Hopf ring is an object in the category of graded co-unital, co-associative, commutative coalgebras, and as such, one consists of a sequence of abelian groups, M sub I, together with a coproduct on each of those abelian groups, and a graded multiplication, here denoted with a circle product. And one place that Hopf rings arise in homotopy theory is in the study of omega spectra. So suppose we have some omega spectrum G. This represents a generalized cohomology theory, with the cohomology of a space X being equivalent to the homotopy classes of maps from X into G. And since the G cohomology of X, these are going to be abelian groups, this means that for spaces of the spectrum are going to have an H space structure, here denoted with a star, and this H space structure gives rise to a product in homology. So if we require that our homology has a Kunath isomorphism where the space is GK, making the E homology of GK a coalgebra, then this will endow the E homology of G all of the structure of a Hopf algebra. So this is great, but we can ask for even more structure than this. We can suppose that our spectrum G is in fact a ring spectrum. Then in this case, the cohomology of a space X is a graded ring, and this will have a corresponding multiplication that will denote with the circle product on the spaces of the spectrum. And then on applying E homology, we get a product, which makes the E homology of G a Hopf ring. So an idea pursued by Ravenel and Wilson was to use these two products, the star and circle product, to produce many elements in homology from just a few. And they applied this approach to compute the mod P homology of classical Eilenberg-MacLean spaces, the Hopf ring for complex cobordism, and the Morava K-theory of Eilenberg-MacLean spaces. So the example we're going to focus on today as motivation for the equivariant computation is this mod P homology calculation of the classical Eilenberg-MacLean spaces. So if we want to talk about Eilenberg-MacLean spaces, it's good to set our notation for that. So we're going to be considering the Eilenberg-MacLean spectrum, HFP, associated to the group FP, and we'll denote the spaces of that spectrum simply by Kn. And up to homotopy, HFP is characterized by the cohomology of a space X being equivalent to the homotopy classes of maps from X into your space Kn. And this gives rise to a star product. Moreover, HFP is also a ring spectrum, so we have a circle product. And ordinary homology with FP coefficients has a Kunath isomorphism, so we have all of the structure needed to know that the homology of these classical Eilenberg-MacLean spaces is a Hopf ring. So that's great, but if we really want to understand this, we want to know what Hopf ring is this. And Ravenel and Wilson use a number of tools to compute this explicitly, and perhaps the most important of them is the bar construction. So I'm going to be using a particular model of the bar construction today, starting with a slightly non-standard model for the topological n simplex. I'm going to let it be points taken from the interval -1 to +1, so that when we introduce a C2 action later on, the simplex can rotate around the origin, which is simply convenient for modeling purposes. Now, this bar construction takes a topological monoid and produces a space. And what's significant about this is that it is a de-looping functor. So what that means is if we apply the bar construction to an Eilenberg-MacLean space Kn, we will get the nth plus 1 Eilenberg-MacLean space. So we have a way to inductively construct these. But what exactly is this bar construction? Well, one model for it is to consider a point, to think of a point in this bar construction as we have some point in our simplex, which is points in the interval -1 to 1. So we'll label these points coming from our simplex T1, T2, T3, and we can think of these as taking labels in our monoid A. So this has some labels A1, A2, and A3. And the space is topologized so that if these points were to come together and collide somewhere in the interior of this interval, you would multiply the labels. And if they were to slide off to the boundary, the label would get identified with the identity in your monoid. And this model is useful because it allows for a very explicit description of the star product. Specifically, if we have some other point in this space, choose a simple one. So maybe we have one with just one point in the simplex and one label. The star product is given by simply overlaying the two intervals. So we then have T1, T2, T4, T3, and the labels all come along as well. Okay. So we have a way to inductively describe these spaces, but what we're really interested in is homology. And one tool to compute homology is a spectral sequence. And associated to this bar construction, there is the bar spectral sequence. So one thing we can do is take this bar construction and filter it. And this leads to having associated graded pieces, which are T spheres smashed with T copies of A. And on applying homology, we get a bar spectral sequence, which computes the homology of BA. So some things that are useful about this bar spectral sequence is that the E2 page of the spectral sequence is given in terms of Tor, which in a number of cases we know how to compute or are easy to compute. Specifically, Tor over an exterior algebra is divided power algebra on the suspension of the generator. So here E1 is the suspension of X, and Tor over a truncated polynomial algebra is exterior on the suspension of X, tensored with divided power on X. So something that's helpful to recall here is the homology of the first Eilenberg-MacLean space. So in the case that we're at the prime 2, this is RP infinity, and then at odd primes, this is a lens space. And this homology is exterior on a generator in degree 1, tensor with divided power algebra on a generator in degree 2. And since we are in characteristic P, this is equivalent to being exterior on E1, tensor a truncated polynomial algebra on generators gamma p to the I of alpha parentheses 0. So recall that a truncated polynomial algebra is fp adjoint x mod x to the p. And these are maybe not the nicest names for generators, so we'll simply call these alpha parentheses I. So at least in the case where we're starting with K1, and maybe we want to from there compute the homology of K2, what we have so far is a spectral sequence that we can compute the E2 page of. So we have gotten part way in our goal towards computing the homology of the next space. And in general, we might hope that maybe the homology only has exterior and truncated polynomial parts so we can iteratively apply this process. But of course, the E2 page is not the end of a computation. So we need some additional tools. And there's structure that we haven't yet used, namely the circle product. So the circle product is induced from a map going from Km and Kl to Km plus L. And this can be constructed very explicitly by induction on M. So since this is an inductive construction, I should probably give you the base case. So that's going from K0 cross KL to KL. And K0 is simply FP. So that will be some number circled with some point in Y. And this will be simply Y, where you take the star product of itself Q times. So with that as our starting point for the induction, we can assume that the circle product on M and L has been defined, and then we replace Km plus 1 and Km plus L plus 1 with their bar constructions as in the last displayed line. And we define this circle product by keeping the point in the simplex the same and taking the circle product on spaces Km and Kl, which is something we already know how to do. And what Ravenel and Wilson proved is that this construction is both well-defined and in fact does recover the cup product pairing in this bar construction. And this is incredibly useful because this construction also factors through the bar construction. So on associated graded pieces, we also get an inductive description of the circle product. And this leads to a pairing in the bar spectral sequence. So if we have a bar spectral sequence and also a circle product in homology, then there's going to be a pairing where on the E1 page of the spectral sequence, the description of the circle product pairing is very explicit, given in terms of circle products and the iterated reduced coproduct. So what to take away here is that if we're trying to compute the homology of the Km plus L space, we can do so by taking elements that appear on the E2 page here and identifying them in terms of elements we already know. And this pairing gives a very explicit way to do that. So in an example, if we're starting with the space K1, which we have the homology of, then we would write down the E2 page for this spectral sequence. And this is going to be Tor. And the exterior portion is going to lead to a divided power algebra on the suspension of E1. The truncated polynomial portion will lead to exterior portion and a divided power portion. So then from there, we're going to identify the permanent cycles in terms of circle products. So one uses the bar spectral sequence pairing to show that this divided power algebra is in fact truncated polynomial on the circle product of alpha i's. Circling with E1 is the same thing as the suspension of an element. And then these generators have some new names. These are called beta parentheses I, and these are coming from taking KZ2, which is CP infinity, and mapping it to KFP2, and comparing the bar spectral sequence. The bar spectral sequence here collapses, which tells you it collapses here, and these give us some additional generators. And so the upshot of this process is that it ends up being the case that we can identify everything on the E2 page in terms of circle products in homology that we already know. And this allows us to inductively deduce the homology of the Eilenberg-MacLane spaces using standard homological algebra. So what answer do Ravenel and Wilson arrive at using this process? Well, letting E1 be in the degree 1 homology of K1, alpha I in the 2I homology, and our generators beta I living in 2I of CP infinity, then our generators are going to be E1 alpha parentheses I defined as alpha P to the I and beta parentheses I defined similarly. And then you need a fair bit of notational indexing sequences, but then they show that the homology of these Eilenberg-MacLane spaces is exterior on circle products of these generators tensored with truncated polynomial of circle products on alpha I and beta I. At the prime 2, this can be written exclusively using circle products of elements in the homology of RP infinity. So this can be written in terms of just the E1s and the alpha i's. And this is something we'll see mirrored in the equivariant case. And then this unstable answer can also be stabilized to the dual steam-rod algebra. So the beta i's can be suspended to define the C i's, and the alpha parentheses i's to define tau i's, which leads to the dual steam-rod algebra. So at this point, are there any questions about the non-equivariant computation?
I wanted to ask something about the upshot.
Yes.
Can you kind of say a little more? So you're saying that you can use these tools to compute the homology of Eilenberg-MacLane spaces using standard homological. So you're not like already assuming this, for example, the Steenrod algebra knowledge.
No, you're not. You're not assuming knowledge of the Steenrod algebra at all.
Okay, got it. Thanks.
Yeah, you're just saying that, okay, we can get the E2 page of this spectral sequence and then use circle products to identify everything on the E2 page and know that those are permanent cycles and the spectral sequence collapses. and then also use hot ring structure to solve any potential extension problems. Okay. So transitioning to the equivariant case, we'll now be considering ROG graded homology. So in this setting, G is allowed to be a compact Lie group, and we consider real representations of G and form representation spheres by taking the 1-point compactification of V and grade our cohomology on the real representation ring of G. So in this talk, we'll be considering a very small group. We'll be considering the group G is cyclic of order 2. And in this case, there are 2 irreducible representations, the one-dimensional trivial representation and also the sign representation. And when we 1-point compactify these representations, we get 2 types of spheres. We get the ordinary 1 sphere, and we also get a sign sphere denoted as sigma, and this sign sphere has a conjugate action. So our grading for homology is then on these 2 types of spheres. We denote that with a 5-point star, and we'll take coefficients in the constant Mackey functor F2, which is the analog of the field F2. So the first thing one encounters when doing equivariant computations is that the ROC2 graded homology of a point is much more complicated than the homology of the point in the non-equivariant setting. Specifically, it's an infinite dimensional non-Noetherian ring, and it has a few distinguished generators. The generators A, U, and theta. So A here is living in degree minus sigma, U is living in 1 minus sigma, and theta in degree 2 sigma minus 2. So what these 2 pictures are displaying are both copies of the homology of a point. In this first picture, each of the dots represents a copy of F2. And in the right-hand picture, this is simply a more succinct representation where we just remember that there are all these copies of F2 inside these 2 cones. And my axes are determined by the number of sign representations is on the vertical axis, and then the topological degree is along the horizontal axis. So our goal is to be talking about C2 equivariant Eilenberg-MacLean spaces, and similarly to the non-equivariant case, there is also an Eilenberg-MacLean spectrum for the C2 constant Mackey functor F2. And this spectrum has spaces KV, where V is now indexed over sign and trivial representations, and up to C2 equivariant homotopy, the cohomology of a space X is equivalent to the homotopy classes of maps into KV. So this gives rise to a star product. And additionally, HF2 is a genuine equivariant ring spectrum. And for this reason, we also have a circle product. So we can try investigating these 2 products and hope that we'd be able to construct a number of elements in homology in a similar way. So the general strategy here is to give explicit models for the star and circle product in this equivariant setting, and then investigate the ROC2 graded bar and twisted bar spectral sequences. And doing this, we recover computations of the homology of K sigma and of KZ rho. So this is a twisted version of CP infinity, and also are able to compute KZ2 sigma. So here Z is the constant Mackey functor, and rho is the C2 regular representation, which means that rho equals 1 plus sigma. But in computing these twisted bar spectral sequences, one runs into a great number of differentials, And so it becomes a difficult computation. So it's useful to use yet another equivariant tool. And this is a lemma due to Behrens and Wilson, which says that suppose we have some C2 spectrum X and some set of elements in the homology of X, such that on the underlying level, they form a basis for the non-equivariant homology of X. And if we take geometric fixed points, we also get a basis for the geometric fixed points of the space X. Then the original ROC2 graded homology that we were interested in is free over the homology of a point, and moreover, the elements BI form a basis. So the computational strategy that I use is to use circle products to produce elements in the homology of KB, and then use the explicit models for the star and circle product to analyze the maps to the underlying and fixed points. So what does this look like? Well, let's begin by following the Ravenel-Wilson techniques. We need to be able to construct our spaces, Eilenberg and MacLane spaces inductively. And to do that, we need a definition. So we'll say that a C2 space is a twisted monoid if it's a topological monoid in the non-equivariant sense, and also has a product satisfying that the non-trivial element of C2 acting on a product is the same as that element acting on Y times that element acting on X. And applied to a twisted topological monoid A, there's a notion of a twisted bar construction. And this twisted bar construction is similar to the non-twisted version, or analogous in the sense that when we apply it to an Eilenberg-MacLane space KV, it gives us a sign de-looping. So we get the V plus sigma space. And it's also constructed similarly in that we can model it by, again, having points in our simplex with labels in our twisted monoid. And then the non-trivial element of C2 acting on this point will take us to the interval will flip around the origin. So T3 will be sent to negative T3, T2 will be sent to negative T2, and T1 sent to negative T1, and gamma acts on the labels as well. So this gives a very explicit model for the signed bar construction, and the model for the star product works the same way as in the non-equivariant case. And once again, we're interested in computing homology, so we're probably interested in the spectral sequence that arises from this construction. And we can once again filter the construction. And this leads to associated graded pieces that are now a little bit more complicated. These are now representation spheres smashed with T copies of A that have an action on them. But on applying homology to these filtered spaces, we do get a bar spectral sequence computing the homology of B sigma of A. And in some cases, this turns out to be fairly computable. So one such example is in computing the homology of B sigma of K0, which is K sigma, which is the same thing as twisted RP infinity. So this is the space of lines through an infinite number of copies of the regular representation. And The E1 page of the spectral sequence looks like when we take our filtration T equals 0, we have a single copy of the homology of a point in degree 0. So that's at filtration 0. So one thing in considering ROC2 graded spectral sequences, the filtration degree is typically not drawn on one of the axes because you already have both axes given to telling you the number of sign representations and the topological degree. And then if we continue going up in filtration, at filtration 1 of the spectral sequence, we get a copy of the homology of a point in degree sigma. Filtration 2, we get a copy of the homology of a point in degree rho, and so on. And something we can recognize is that in this example, the filtration degree actually corresponds to the topological degree. So here at T equals 0, T is 1, T2. And what this means is
do the overlapping triangles just mean
they're
like
just
you
on
have
they're on top of each other.
got it,
So,
okay, thanks.
Yeah.
Cool.
So because a DR differential shifts degree down by at most 1, we can't have any DR differentials greater than 1. And additionally, so that leaves just the case where perhaps we would have a D1 differential that looks like this. But if that were the case, then we'd kill off this entire double cone. And we know the homology of the underlying space is RP infinity. And if we killed this off, we would then have nothing left in degree 1, which would be a contradiction. So we can't have any non-zero differentials, and the spectral sequence collapses. If we work a little bit, I'll give some of these names, since I'll call this generator E sigma, this one alpha, alpha parentheses 0. In analog to, in the non-equivariant case, we have E1 and alpha parentheses 0. And if we work a little bit harder, we can also determine the product structure and show that the homology of the space is exterior on these generators E sigma and alpha bar parentheses I living in the 2I rho degree homology, and also determine the coproduct, which has distinguished elements A and U from the homology of a point showing up. So the formula for the coproduct is a little bit more complicated than in the non-equivariant case. So there are other examples in which the twisted bar spectral sequence also collapses for degree reasons, where like in the picture, we had this nice gap. And some of these examples include twisted CP infinity and also KZ2 sigma. However, in general, if you wanted to continue using the twisted bar spectral sequence approach, so this is a picture of the E1 page of a spectral sequence which is converging to the homology of B sigma, K sigma. And here we have, you can see in this picture, it's much more complicated. There are D1 differentials and hidden extensions, and also D1 differentials, which induce higher differentials. And as one goes further out in the spectral sequence, the behavior is much more complicated. And it's also difficult to show that the differentials do exactly what you would hope. So this is not the easiest method of computation. So that's motivation for using the Behrens-Wilson computational lemma. And in order to use that lemma, it's helpful to know the fixed points of the equivariant Eilenberg-MacLane spaces. So there's a proposition due to Caruso, which says that if we're looking at the M sigma plus nth Eilenberg-MacLane space, the C2 fixed points of that space is going to be a product of non-equivariant Eilenberg-MacLane spaces. And what he shows is something actually a little bit more general. He shows a similar formula for CP fixed points. So in a particular example, if we're looking at the homology or at the fixed points of K sigma, this is going to be a copy of K0 times a copy of K1. So in an example of using the Behrens-Wilson lemma, we would need to show that we need to understand how this homology maps to the underlying and fixed points. The homology of the underlying is exterior on a generator E1 and generators alpha parentheses I, and the homology of the fixed points is exterior on generator E0 in degree 0 to account for a copy of K0, E1, and alpha I. So then one needs to understand these two maps, and it turns out to be the case that to the underlying homology, the E sigma simply maps to the E1, the alpha bar i's get unbarred, and in mapping to the fixed points, the E sigma maps to E0, and these bar i's are shifted so that alpha bar 0 maps to E1, and then the rest of them get unbarred with a shift of index. And understanding these maps gives an alternative proof to this computation that the homology is exterior on these generators, as long as you knew that these generators existed. So one can use the Behrens-Wilson computational lemma to produce the homology of the K sigma spaces and take finite indexing sets and look at circle products of elements E sigma and alpha bar i's, and then understand where those map on the underlying and fixed points levels. That shows that the homology is in fact exterior on these generators. And this answer mirrors the non-equivariant answer at the prime 2. Further, having very explicit point set level models also means that we can analyze how the circle product factors through the bar construction, again, in the equivariant case for these equivariant Eilenberg-MacLane spaces. And it turns out to be the case that you can once again inductively define the circle product map on the associated graded pieces. And this leads to a spectral sequence pairing where you do need the additional, you do need to know that you have sufficient freeness or flatness in order to get this pairing. But as long as you have that, you once again have a pairing on the E1 page, which is given in terms of the iterated reduced coproduct. And you can use those pairings to show that the homology of K rho is exterior on some, in the case so non-equivariantly, we had some generators beta I, those were coming from KZ2 mapping into KF2. And now we have the same sort of thing showing up equivariantly, where now these are Mackey functors, and that's how we get additional generators beta bar I, and the homology of K rho is exterior on a mix of generators E1 and alpha I coming from non-equivariant homology, circled with generators in K sigma and these new generators beta bar I. And from here, one can continue applying the bar spectral sequence in order to get the homology of all of the spaces K sigma plus I.
Nick,
And it takes,
can I ask,
yes,
could you go back one slide?
yes.
You mean on that last formula, do you want an H star on the right? That's-
On the right,
What does that mean?
this here.
Yeah.
Well, so I guess I probably want to say this is exterior on these.
Okay.
Yes,
Okay.
thank you for that. Okay, so then it takes a fair bit of notation to say what are the right sequences of circle products, but one can write them down for all these spaces K sigma plus star. And continuing from there, well, you'd want to consider spaces 2 sigma plus, and one totally can do that, but the circle product generators, naming them well becomes increasingly difficult. So you can compute that the homology of K2 sigma plus 1 is exterior on this set of generators, where this first column of generators corresponds to the K1 fixed points. The second column on the fixed points level gives you K2, and this third column gives you K3, and then all together on the underlying, it gives you K3. And one thing you'll notice is we have these generators phi K of E sigma circle E sigma, and these are new generators appearing in this space that can't be named in terms of circle products of generators in other spaces due to degree reasons. So one can prove that the homology of the spaces 2 sigma plus I is exterior on generators given by taking circle products of generators in non-equivariant homology with generators in equivariant homology, and there's some specific indexing conventions that will tell you which of these generators this should be. And more generally, the ROC2 graded homology of KV, where 2 sigma plus 1 is contained as V, is exterior on generators given by the cycles on the E2 page of the ROC2 graded bar spectral sequence. And one shows that using Hofring structure on the ER page to eliminate non-trivial differentials. So some additional questions that I am interested in investigating next with this project include, so non-equivariantly, you can stabilize the unstable answer to get the dual Steenrod algebra. I'm interested in how the stable relation in the equivariant version arises unstably, and then also other equivariant analogs of Ravenel-Wilson computations, particularly with Neal-Brown-Petersen spectra, understanding the algebra of twisted bar spectral sequences better, and the ROC2 graded. So this answer is an ROC2 graded bicommutative Hopf-ring. There are also C2 equivariant Brown-Gittler spectra, and I'm interested in if a type of Dieudonné theory can be formulated C2 equivariantly, what that should be, what properties that should have. So lots of questions for next. And with that, I'd like to wrap up my talk.
All right, let's thank